I'm sorry about the prior video. I was stating that the voltages in the circuit are minuscule and nothing to worry about electrocuting yourself while the field itself is very strong. That's not true. It's not entirely true. It's only true for the area of the circuit that could be useful to carry a load. And that it would be like in this area in here where the battery is, or maybe to some degree where the coils are located, because the differences in voltage across the two terminals of each component is like minuscule. So the voltages are all evened out. But this is not where the voltage gets generated. Even though we have a battery here, that just charges up the circuit with a minuscule amount of energy. It's produced in the spark gaps, in particular, not so much the left one, so much as the right one. Especially, this capacitor up here holds a lot of charge, and then these two side capacitors hold almost as much charge as this one does. So if you want to consider danger, it would be these three capacitors up here. Well, all the capacitors, because they store charge. So they'll develop a voltage difference across their dielectric. So they're dangerous. But the ones over to one side are going to be more dangerous than the other side, apparently. That might just be a fluke of the simulator. But be that as it may, there is danger. It's just not usable danger. Because the minute we try to tag a load to here, it collapses the production of energy, the amplification of energy, and so you end up with nothing. So you can't kill the goose that lays the golden egg by directly attaching or immediately attaching nearby to it your load. You've got to have several layers of insulation, so to speak, buffering your production area from your consumption area. Otherwise, your production will flatten out and go neutral, and you'll be left with nothing. So that's the toss-up in this circuit. It's not a very efficient circuit in which we're wasting a lot of voltage that we don't get to use, but we have to amass that much excess of voltage in order to come up with something elsewhere that we can use. So if I bring back the nodal voltages, just to show you what I mean. So VTC10, vacuum tube capacitor number 10, 80 million volts negative on the top plate, and positive 673 volts on the bottom plate. That's a big difference. That's close to 80 megavolts difference between the two. Then when we go to this capacitor plate, we got 80 on one side, but we have 24.25 meg on the other side, so there's not as much difference between these two plates as there is between these two plates. And then this one is the same situation, 80 and 24. So if we look at the schematics that I generated recently, back up here. So I did it in RMS, and so this is the top one of the next three schematics. This is VTC10, the topmost capacitor, and this is VTC8, either 8 or, well, I took the one to the right. I could have taken the one to the left. It's the same value. So, is this the right one? Nope. Here. So, here's VTC10, and here's VTC8. I could have done VTC7, but it will be the same as 8, so we'll leave it at that. So this one is the voltage. So here we've got VTC10 is the voltage up here. What is that? That's 75 megavolts RMS. And then VTC8 is slightly over 25 megavolts. So we're dealing with a lot of voltage here. The current, on the other hand, is something else entirely. Here's VTC10 again. Here's VTC8. So they're very consistent in their power levels. 10 is greater than 8. So here it's somewhere in the vicinity of either half or the same as this line, which is 3.2 micro amps RMS, 3.2. And then VTC8 is hovering around 1.6. Where's my finger? Finger. 1.6 microamps. So the voltage is in the megaamps, but, the voltage is in the megavolts, but the amps is in the microamps. So as you can guess, the wattage is over 200, let's say 230 watts on VTC10, and that looks like it could be 50 watts on VTC8. So the wattage is, reasonable for not an EV. I don't know what that's reasonable for. Wattage. That's wattage for a light bulb. So you could light a light bulb within 500 seconds of accumulated energy. Maybe. If your light bulb could withstand the voltage of millions of volts, then yeah, you could probably get away with it. But I thought I'd bring this up because, yes, there is danger in the circuit. I shouldn't say there's no danger. There is danger in certain areas of the circuit. But the power you end up being able to get out of it is next to nothing, and so I didn't make charts for that because it's very embarrassing. But, there's a part of me that wants to chug on and not worry about these shortcomings because I have faith I'll come up with something better. But at least I'm getting to be more realistic. So I'm using Gear method of approximation, which is not as beneficial or pretty with big numbers output as is trapezoidal method of approximation. I have had to raise the bar as much as I could for how much divergence I can allow the simulator, but it does have its limits, so that's why I can't show you any higher values. Not to say that it doesn't go, but the trend is, it goes to infinite gain, so if it hasn't fried itself by now, it certainly will in short order. And so it takes 500 seconds as opposed to 200 seconds or anything less than 500 seconds. Due to what fact? I tried to make improvements, so I changed, the first thing I did for realistic sake was I took out the transformer and I put in my own makeshift transformer of two lumped coils with a mutual coupling between them of, I think it was 99%. And I found I could get a gain if I made this coil 1,000,000 times greater inductance than this type. Well, usually you can't get 99%, so I'm fudging here. 99% coupling coefficient with that much divergence between two coils. And it won't be easy to wind them. How do you wind something like that? But I did do one improvement. I chose to dispense with the 25 gauge wire and switch to 4 zeros. 200 AUG, which is the lowest I could find a wire chart for. And the resistance is nice and low. It's something like 1.5 milliohms per, I think it's 31 feet. See, I had to use 31. First I had to figure out, what is 1 ohm of inductance on a 25 gauge wire? Because I forgot what it is, I don't keep track of these things all the time and stick them up in my brain. I don't have perfect memory. So I had to refigure it, and I came up with a figure of 31 feet per ohm of resistance at 25 gauge wire. So then I used the calculator on the web to determine, what would the same length of wire be? What would be the resistance if it were 40 gauge? And that gave me 1.5 milliohms per 31 feet. So I'm assuming that being that the length is the same, the inductance will be the same as well. That's usually the way I work it. Of course, the turns won't be the same, obviously. You may not even wrap it around once. With that thickness and that length of 31 feet of wire, I don't know. Maybe you could wrap it around once, I suppose. For 1 Henry, I don't know. I don't know if you can. See, those are a lot of presumptions on my part. I just wanted to look at resistance, and I just I'm looking at extremes here. Okay, so I'm not exactly realistic. I am looking at extreme limits, at least insofar as what the simulator can tell me, not what somebody could build necessarily. Because I want to see at least some measure of limitations, whether or not they're reasonable ones, to at least have an idea of, well, okay, I really can't go beyond that limit, you know, even though it may not be buildable. I can't think beyond that limit of any remote possibility. Unless you made your own custom-made wire, I don't know how you'd wind it though once it gets that stout a girth. How do you possibly wind the damn thing? Even if you could have a machine to wind it for you, press it into place, maybe mold it into place, you know, extrude it into place. I don't, while it's still hot, might have to, or reheat it while you're winding it. Ooh, that'll be fun. Whoops! See, there went the insulation. So I don't know. If this makes any sense to any of you, but the point of this video though wasn't realism. I just showed you. So there are 3 different versions of this circuit now: F, G, and H. For I think it's what is it? V8B2. And so this is the latest one, the H version. There's also a G version and an F version. H is in Harry, G is in George, F is in Frank. Because each time I made changes to this transformer. So first I took out the transformer and put in 2 lumped coils with a 99% coupling coefficient between them. And then I raised the inductance on the right-hand coil from 1 microhenry to 1 henry, and then I changed the gauge of wire from 25 gauge to 40 gauge. And the first of those changes was to try to induce realism, and then the second and third were enhancements to try to raise the voltage because it wasn't looking too good. And I raised it to the max of what the simulator would allow me to simulate, and that was 500 seconds. So obviously it's an excess of voltage. If we're looking for voltage as the target, it sounds like it's a little excessive, to put it mildly, but at least the simulator allowed me to go that far so I could at least see what is going on. It is always nice to see. It's the whole point of the simulator, is otherwise why bother using it? Just to get a vague idea, you know, a broad idea. It's, you know, don't take it too literally, because if you did this circuit, if you could do this circuit in LT Spice, you would get slightly different answers at the best. You could get drastically different answers at the worst. Even though they're both running Berkeley Spice, it's their own way of implementation that makes all the difference, and various policies that they institute that forces you to make changes to the circuit so it's not the same circuit anymore. You know, I couldn't do this in LT Spice, no way. It'll have me putting grounds all over the place, and that'll either ruin the circuit or it'll make it worse and less manageable if I steer clear of the worst case scenario by using capacitors, not resistors, between the circuit and ground. Once I start putting in extra capacitors, the whole thing just explodes in your face, and there's no way to manage it. So that's why I stay away from LT Spice. And I don't have to use it because microcap is now, it's given away for free. So why not use it? The problem is, none of these things are designed for over-unity circuits that explode with an explosive force of over-unity. So it's hard to imagine, it's hard to take it seriously. So I just use this as a broad guide, so that if I had to build this tomorrow, how would I start? You know, what would I start, what could I presume to be the ballpark area, you know, the kind of rough estimate area of what kind of values to my components would I be looking at trying to purchase. So I tried to keep those things realistic. Yet there are other things going on that are not realistic, and so there's only so much I can do here. What else? So I still can't answer the question, what's it good for? And I wish I could. What's the point of having all this voltage and no amperage? What's the point? I don't know. Oliver Heaviside would obviously have a fit because the message would not get sent overseas. It would not reach the Atlantic or coast of America if sent from wherever it was sent from in Europe, because voltage would show up, but the current would not. It would either lag behind or not show up at all, and you'd end up with a garbled message. If at the worst, at the best, you get a delayed message. Might take a week or two to show up. I mean, literally, that's what happened. And then it just kept getting worse and worse until finally it didn't show up at all. Just a mess showed up is what showed up. And this was telegraph, dots and dashes, you know. It's not like it was voice or high fidelity or something. But this was 150 years ago. That was technology of that era. So that's basically the situation I'm finding myself. What would be the Heaviside solution to this? Make all the wire and the coils not strictly copper, but make it insulated copper, which it already is, but wrap iron ribbon around it, insulated iron wire around the copper wire core, and then wrap your coils, and then connect all your components? Maybe that's what it takes. But how do you show that in this simulation? As it is, I had to take out inductors over here to raise the voltage, because I wasn't getting as much voltage rise as I would have liked within the time frame that the simulation ran for. So I've already taken out inductance, if there ever was one. It's certainly not in there now, but it really is. I didn't lose a whole lot. It was negligible to begin with. It's got this set amount of 9 nanoamps in this area up here, so it's, nothing's changing much. Only the voltage changes, and the amps pretty much stays the same in this area within the time frame that the simulator allows me to work within. So I don't know what the solution is. I guess the Heaviside solution would be to do that. Wrap all this wire and the coils with iron wire, which means that you almost don't have to, in a sense. I don't know how you would simulate that. Trust me, I'm already clueless just thinking about it. You could put a transformer in series with this up above it, I suppose. One's copper and the other's made of iron wire. Despite the fact that only one thing I'd know in advance, the iron wire would have higher resistance than the copper windings on each transformer coil. But what's the magnetism? You wouldn't have to make so many turns, or you would have to use the same mass, maybe, or the same number of turns. I don't know. To do what? You'd get more inductance. So I have no idea how to guess estimate how to solve this thing. But if I had to do the Oliver Heaviside method, that's what I guess I would start out with. This whole thing would be bifilar. One would be copper, the other would be iron, and the iron would be coiled or wrapped around the copper wire. And then, of course, that bundle then has to be insulated with, or shielded, actually. You're going to have to shield that to ground, and I'm not sure whether you'd use an electromagnetic grounding of 2 points at either end or an electrostatic grounding of just 1 point at one end. I don't know. Probably I would guess electrostatic, not electromagnetic, because I'm trying to build up magnetism here, the magnetic field. So I would probably not use a double grounding at either end, or whatever constitutes the either end in this case. Probably just a single end, because I think I'd have more to worry about the electrostatic field building up in excess rather than the magnetic field building up in excess. I'm trying to encourage the buildup of the magnetic field, so I hardly want to ground that. So it'd be a single wire grounding probably on somewhere, and that's just the shielding on the cable, which in this case happens to be the chassis of the car. So is that the part that I'm missing? Because now if we go to William Lyne and his 18th chapter of Pentagon Aliens, or Space Aliens from the Pentagon, his earlier edition, he talks about, he talks about something that even, I can't remember the guy's name who wrote the 63-chapter book on Nikola Tesla's writings and inventions, published in 1894, a year after Tesla's demonstration in the agricultural building of the Chicago World's Fair in 1893, and then the fire, his lab fire, that destroyed all evidence of what he was working on, his special generator, in 1895. What William Lyne offers us is a little bit of insider information that he got from somewhere. What was I going to share with you? When it was applied to, when Tesla's special generator was applied to the Nazi electro U-boats, that Germany had in World War II, the chassis of the generator was bolted to the floor of the U-boat, and in that room that generator was bolted to the floor of was contained the battery bank, the DC battery bank that generator was going to recharge using compressed air to drive the generator, very little, stored in liquefied air tanks, by comparison to the diesel fired up generators, that they could only run if they surfaced, and of course that put them in risk of enemy fires. So they had to wait until they were in peaceful waters to recharge their batteries. Otherwise, they were dead in the water. They couldn't go anywhere. They only had so much charge on their DC battery bank, their battery banks, to run their DC motors. So the purpose of that special generator was merely to recharge the batteries. And it ran off of very little compressed air, so they could store enough compressed air in liquefied format to last them a good 30,000 miles of range before they would have to recharge the compressed air tanks with liquefied air, probably by running some kind of DC motor-driven air compressor, and then some kind of pre-chilling, to swap out the temperature to make it easier to compress. Flash condense, like a Stirling cycle heat pump. So that's where we get the idea that the hull of the vessel is a massive amount of steel. Oh yes, the quote. I knew there was a point to this. He quoted Tesla as saying, for every pound of iron added to his device, namely his special generator, 1 horsepower was increased of its output. Was it a pound of iron? Or was it a ton? No, 200 pounds, excuse me. For every 200 pounds of iron added, coupled to his device, magnetically coupled to his device, 1 horsepower was increased. So that's why I always felt that's why he chose a Pierce Arrow, because it weighs 4,000 pounds. Maybe 3,000 of that, or 3,500, is actual steel in the chassis. I don't know, maybe 2,000. If we wanted to be really liberal, we could say 1,000. So that's a lot of steel. Magnetizable steel, hopefully. So that's what we would be hoping for. And with the chassis of the circuit bolted and magnetically coupled to the chassis of the Pierce Arrow, we could stand to gain a good deal of... See, that's the Oliver Heaviside correction. That's it. See, I make a video and I come up with my own answer. That's it. That's the Oliver Heaviside correction. Is the magnetizable hull of whatever vessel we're using to move around in with this kind of circuit that only generates voltage. This circuit. Not to say his special generator produced only voltage. But when I think about it, yeah, because the M coils on that thing were massive and long, even though they were thin gauge wire. But the H coils, the magnetic coils on the reciprocating piston, which also rotated, is minuscule amperage. So that's right, that was basically a voltage-oriented device. And if you're recharging batteries, that's all you need is voltage, right? Well, no, you need some current. But if you're connecting it magnetically coupled to a massively magnetizable hull of a vessel, I mean, huge tonnage on that thing, now you've got yourself the Oliver Heaviside solution. So that's it. So now I can feel better. Whew! See, it's been quite a while, before I started out on this odyssey of studying the simulation of free energy circuits, and the simulation can't tell you everything. So you got to interpret what limited information you're getting out of the simulator, and then know how to add in the additional information, the clues that we have, the historical clues, to help piece together, well, what could a person do 100 years ago, based on technology dated from 100 years ago, because we've been stalling, dragging our feet on this free energy for a century, at least a century, actually longer than a century. But if we only go back a century, that's bad enough. That's pretty bad, because that's when research pretty much stopped. Electrical research pretty much stopped a century ago. And that's what Eric Dollard says, and I have to agree. That's what the evidence provides us with. So that's the solution to this high voltage circuit. And that's why I want to hold on to my car so badly, because it's a 3,000 pound car. I don't know how much of that is magnetizable mass of iron, but it's certainly a lot, probably. It's certainly not composite, and it's not aluminum. So that's the correction. So we have to bolt it to the frame of the car, and we have to have an aerial to carry off charge in the form of ionization of the air passing across the aerial, or else force it through a manifold internally with more surface area, so that we can more readily ionize that air and get it out of there, more strongly ionize it, more volume of air ionize it than this skimpy little aerial. Yeah, that's the answer. That's it. Okay, now I can shut up. I feel better now.